Section 7.2 is about interpreting correlations. Here are our learning objectives. So the correlation coefficient is calculated to be at R equals 0.008 for this data set. What kind of correlation is this? Well, that would be positive. You can't see the blue. Let's try again. Positive. And I could consider that strong, right? That's strong correlation. What would happen, though, if we cover up this data point in the upper right corner? Then what happens to the correlation? Well, now it looks like there's no correlation, right? That value up here, that little blue dot I had originally, that is an example of an outlier. And it can really affect our data when we're looking for correlation. So let's say you've conducted a study to determine how the number of calories a person consumes in a day correlates with time spent in vigorous bicycling. Your sample consisted of 10 women cyclists, all of approximately the same height and weight. Okay, cool. Accounting for variables, good ideas. Over a period of 2 weeks, you asked each woman to record the amount of time she spent cycling and what she ate on each of those days. And you used the eating records to calculate the calories consumed each day. Figure 7.1 shows a scatter diagram with each woman's mean time spent cycling on the horizontal axis and the number of calories they took on the y-axis. Do cycling times correspond to a higher intake of calories? Let's look at this graph. So it does appear, if you look at the data as a whole, it's probably going to tell you there's a positive correlation, right? But this correlation is very weak. Like if I was going to draw a line, it's weak because all the points are pretty far away. Like it'd be like an R equals like 0.3, right? That's pretty weak correlation. However, if we were to say take away these two outliers, we'll erase them in green, and draw our line again, now it looks like there's a stronger positive correlation, right? And it was affected by these two outliers. Maybe those were invalid data points. I don't understand how anybody could bicycle this long and eat that many calories. Or maybe this was a fluke. This woman cyclist right here. So just be aware of how outliers can really affect our data. Next, we need to consider how data are grouped. So correlations can also be misinterpreted when data are grouped inappropriately. In some cases, grouping data can hide existing correlations. So let's consider this hypothetical, right, not real, study in which researchers seek to find a correlation between the hours of TV watched per week and high school grade point average. So they collect 21 data pairs and we put them in table 7.2. Here's our scatter diagram, right? This shows virtually no correlation, right? Our correlation coefficient is negative 0.063. That's like really, really close to zero. So we can conclude that there's no correlation between the amount of TV watched and GPA. Here's the thing. If you watch a bunch of TV and you don't spend time studying, like our gut instinct would tell us that, man, that should affect your GPA. So let's take a look at how we've been grouping this data. So one of the researchers realized that some of our students in this study watched mostly educational programs, documentaries, Bill Nye, while the other tend to watch comedies, dramas, and movies, which are great, don't get me wrong. But if we divide the data set into two groups, one for the students who watched educational programs and the other who watched regular TV, maybe we'll see a correlation between the amount of TV watched and grade point average. So here we have on the left our weekly TV hours group 1. This is the group who watched educational programs. And then this is those who didn't watch educational programs. I call that like fun TV. So now we see we have a positive correlation, and pretty strong, I would say, um, if in the amount of educational TV you watch and your GPA, versus if you watch fun TV, we've got a negative correlation. So we can conclude that watching not good TV, educational programs can help your GPA, while watching just kind of fun sitcom stuff would not. Let's take a look at example 3. This looks at used car weight and price. So this figure is a scatter diagram of some hypothetical data collected by a consumer group studying the relationship between the weights of cars and the prices of cars. So here I've got car weight on my x-axis and car price on my y-axis. So I'm thinking, okay, that car weight is affected by it. Car weight is an explanation for car price, right? We've got our independent variable and our dependent variable. Just fun to keep all these terms fresh in our brains. So what kind of correlation does this data set show as a whole? Well, as a whole, it would show kind of a positive correlation, but very weak, I would say, because they don't all line up on the same point. But what does correlation for each cluster group show? Well, if you look at each cluster group by itself, it really kind of shows no relation, no correlation. Well, that could be because, SUVs, which weigh more, tend to cost more from the get-go, as opposed to like tiny little cars like my little hatchback cost a lot less. So looking at separating out the different car types could have been really beneficial to this hypothetical study. One thing I want us to note is that correlation does not imply causality. Two variables being correlated does not always mean one variable causes the other variable. Possible explanations for a correlation could be a coincidence. Both correlation variables could be directly influenced by some common underlying cause. And one of the correlated variables may actually be a cause of each other. So you can have true causation. You just need to check that it's not coincidence or an underlying cause. So, like I said earlier, one of my favorite examples is that ice cream sales increase with the number of broken arms in kids. Right. Are the broken arms causing increased ice cream sales? Are the moms like, oh, I'm so sorry, let me go buy you some ice cream? No, this one has an underlying cause. And that underlying cause is summer, right? Once it gets nice out, people buy ice cream, kids run around breaking arms. So keep that in mind. That's my kind of favorite go-to example. So which of, typo, of the possible explanations are most likely for the following? Wow, good job, Lauren. So let's look at A, the correlation between infant mortality rates and life expectancy. Do we think that that could be a coincidence, have some sort of underlying cause, or one could be the cause of the other? Well, for portion A, the correlation between infant mortality rates and life expectancy, that could be due to healthcare, like access to quality healthcare. There's a variable, quality of healthcare, that could be affecting them both. It could also be the neighborhoods you live in that's affecting the quality of your healthcare. Do you live in an area with a lot of manufacturing? So there's a lot of variables that could be affecting each other. Next, the correlation between the increased number of geese and the decrease in ice cream sales. Is that a coincidence? Is that an underlying cause? No. Yeah, there is going to be an underlying cause. The underlying cause is it's getting colder. So like when fall comes, winter, right? We get all those Canada geese driving us crazy. And ice cream sales decrease. And then C is the correlation between time students spend studying and their grades. Well, that's definitely a cause. One is going to be the cause of the other. The more you study, the better grades you achieve.